Hey everyone, in this video we're going to talk about the peripheral control ventilation. Just as a recap, in my last video, if you haven't seen it already, we spoke about the central control ventilation, and this is part of a 3-part series where in the third video we'll integrate it all so we can really understand how these systems interact and what are the controls of breathing. So as mentioned in the first video, most of these systems are a sensor, integrator, effector system, which is also known as a negative feedback system. So in that first video, we talked about central chemoreceptors, which measure or sense the blood PCO2, which then can cross the blood-brain barrier. Then through our normal equations with CO2 plus water becomes carbonic acid, dissociates into bicarb and hydrogen. And it's the hydrogen that we specifically spoke about in the last video that then stimulates our integrator systems, which is our pons and medulla, with the ventral respiratory group and the dorsal respiratory group. Now, the peripheral chemoreceptors are slightly different in that they also sense blood PCO2, but more directly rather than indirectly like the central ones. But they also sense the partial pressure of oxygen in the blood and also pH. And then I'll also at the end just talk about some mechanoreceptors as well for completeness. And then these all go to our integrator, which is in our pons and medulla, which lead to effectors, which lead to changes that our sensors then sense. And it's a negative feedback loop, or in a working system, it should be a negative feedback loop to then maintain homeostasis. So here we have the brain and we've got the pons and the medulla, and remember these were where our central chemoreceptors were as well, but I'm specifically talking about it in the context of the integrator system here. And then on the right we have our heart, and then off the heart we have the aorta. And it's important here, so the aorta has some branches that come off it. And the first one is the brachiocephalic artery, followed by the left common carotid artery, and then the left subclavian artery. And on the right, a branch off the brachiocephalic is the right common carotid artery. And then both of these arteries divide off into an internal and external carotid artery. So just at the arch of the aorta, there's what's called the aortic body. And then around the branching of the common carotids into the internal external, there's the carotid bodies. And these are important, and I'll explain why in a moment, but they're innervated by cranial nerve 9, which goes to the carotid bodies, and cranial nerve 10, which goes to the aortic bodies. So the reason why they're important is they contain different cells to what's otherwise seen in arteries. So just on the left bottom here, we're sort of drawing a diagram of what this would look like. So in red, we've got our blood vessels, and then in purple, we've got type 1 glomus cells. And then in orange, we have our type 2 sustenacular cells. So the glomus cells contain large amounts of dopamine and nerve endings, whereas the type 2 cells resemble glia with a supporting function. And they are innervated, as we mentioned before, by cranial nerve 9 and 10, depending on whether they're from the carotid bodies or the aortic body. And for those of you who aren't aware of the cranial nerves, cranial nerve 9 is glossopharyngeal nerve, and cranial nerve 10 is the vagus nerve. So these peripheral chemoreceptors, it's important here to also mention they've got high blood flow and it's in excess to their weight. So what that means is that their oxygen requirements are met mainly by dissolved oxygen, which means that they're sensitive to the partial pressure changes of oxygen. So they're not going to sense the oxygen that they've already used up and always think that you're hypoxic. The peripheral chemoreceptors, when they're stimulated or activated by whatever stimulus, and that's usually high PCO2, low oxygen, or decreased pH, they block potassium currents and cause membrane depolarization. And this leads to voltage-gated calcium channels opening, and the influx of calcium provokes exocytosis of neurotransmitters. As we mentioned, the type 1 cells have a lot of dopamine and neurotransmitters in them and are highly innervated, which then stimulate the nerve endings and produce action potentials, which then leads to our stimulation of the nerves leading up to the integrated systems in the pons and the medulla. So I've already touched on it, but the stimulus for these are low PaO2 and high PaCO2 and low pH. But it's worth mentioning here that the aortic body is slightly different in that it also senses low PaO2 and CO2, but low pH isn't what it predominantly senses, so it's not very sensitive to pH, but it's the carotid bodies that are. So again, let's just fit this into our sensor integrator effector model. So we have our sensors, aortic body and carotid body, our integrators, which are pons and medulla, and our effectors, which are our respiratory muscles. So low PaO2, usually around less than 60 millimeters of mercury, and high PaCO2, normally greater than 40 millimeters of mercury, and our body likes to keep us, plus or minus 2 from 40. And then the higher PaCO2 will lead to increased hydrogen ions. It's the same equation as what we described in the first video in the CSF, but it happens in the blood, and this leads to decreased pH. But as we mentioned, this is a function of the carotid bodies, not the aortic bodies. And so these stimuli will then stimulate the aortic and carotid bodies, traveling up cranial nerve 9 and 10 to our integrators in the brain, which then leads to increased respiratory muscle stimulation, which then will hopefully reverse the low oxygen by increasing the PaO2, decrease our PaCO2, which will then hopefully also increase the pH, making us less acidotic. And the hope is that this negative feedback will then maintain homeostasis within a range that is set by our integrator system. And just to put it into perspective with our central chemoreceptors, so they're also sensors, but they're more directly linked to the integrator. As we mentioned, they sit within the brain in the medulla. So there are some differences between these two sensor systems. So the peripheral sensors, they're faster, but their response isn't as strong, while the central system is slower, but it has a much stronger response and a more sustained response. Some textbooks will quote it as providing about 60 to 80% of the response. And I mentioned before we'll talk about mechanoreceptors, and I'm just using this as a loose, broad term just to cover some of the other sensors that will affect respiration and ventilation. So the first one is the lung receptors, and there's 3 types. The slow adapting pulmonary stretch receptors, and these are found in the smooth muscle of the trachea and the bronchi. And they're associated with the Herring-Brewer reflex. During steady inflation of the lungs are activated and results in an increase in the duration of expiration when it comes to expiration. So it helps our body know how far we need to deflate the lungs after being inflated. And then there's the rapid adapting pulmonary stretch receptors. And these are in epithelial cells of large airways such as the carina. And they increase their firing in response to the rate of change in the lung volume and cause rapid shallow breathing. They used to, or in some textbooks, will be called irritant receptors as well, just to be aware of. And this is because chemical stimuli such as cigarette smoking was known to stimulate them. They're also associated with a sigh or a sigh reflex, and this is an augmented breath we take every 15 minutes or so. And this action is it's seen mostly in newborns, but it's thought to help open up atelectic airways or alveoli. And then lastly, there's C fibers, and they're also known as J receptors, and the afferent nerve endings of the vagus nerve that lie close to the pulmonary capillaries, which is stimulated by increases in interstitial fluid or edema and by histamine, bradykinins, and prostaglandin released during lung damage. So second, we have joint and muscle receptors, and these are to do with the proprioceptive nerve and muscle bundles, also known as muscle spindles. And we know that if you move your joints and moving your arms, you will start to increase your respiratory rate and tidal volume, and this is likely preempting you about to exercise. Then there's baroreceptors, and these are also found in the carotids and aortics, but they're not the bodies, they're the carotid and aortic sinuses, and they're to do with pressure. So they measure pressure of the blood, and we know that hypotension stimulates breathing, while hypertension can depress breathing, or ventilation to be more accurate. Then there's temperature. It's not specifically a mechanoreceptor, but we know that increased temperature will increase ventilation and respiratory rate, and this is likely through stimulation of the hypothalamus or the thalamus, which is also closely linked to respiration. And then hormones can also increase your respiration. So adrenaline and noradrenaline can increase respiration and ventilation. And we know that progesterone, which is a hormone of pregnancy, can also stimulate breathing. It makes you more sensitive to the changes in CO2. It's one of the reasons why in pregnancy we see increased ventilation, not just because of needing to clear the excess CO2 from the baby, but the hormone itself can also make women more sensitive to CO2. And an off-label use of progesterone is that it has been used sometimes in central sleep apnea to help these people have more stimulus to breathe or be more sensitive to stimuli to breathe. So if I were to draw this into a flow chart and simplify it down, we know that the main driver of respiration and ventilation is our partial pressure of CO2 in the blood. So it goes in the blood, it will cross the blood-brain barrier, which will increase hydrogen ions in the CSF, which we know stimulates the central chemoreceptors, stimulating our respiratory centers, increasing our respiratory rate and tidal volumes. And then in a negative feedback fashion, it will then reduce the PA CO2 to bring us back within that range that our body wants to keep us in. For the peripheral chemoreceptors, it does the same, so increased PA CO2 sensed by our aortic and carotid bodies. It also, through our Henderson-Hasselbalch equations, leads to increased hydrogen ions within the blood, which will decrease our pH. Again, another stimulus for the peripheral chemoreceptors. So this all stimulates our respiratory centers again, leading to increased rest rate and tidal volume. And then a lower PaO2 will also stimulate the peripheral chemoreceptors. And then again, this is a negative feedback loop. So our increased rest rate and tidal volume will hopefully bring down our CO2, and it will also increase our PaO2. Again, highlighting the importance of PaCO2 as the main stimulus for ventilation. However, we mentioned in the first video about chronic elevations in CO2. So when there's chronic elevations of CO2, it will lead to increased CSF buffering, so meaning that our CSF is less sensitive and our central chemoreceptors are less responsive and able to respond to CO2 changes in the blood. The same thing happens in our blood as well, so the blood is now buffered, so there's less hydrogen, less changes in pH. And this will knock off each of these different stimuli, meaning that the only thing left is our lower PaO2, highlighting these people that become dependent on oxygen or hypoxia for breathing rather than CO2. And then these people can have something called CO2 trapping, where because they're not responsive to CO2, CO2 can then build up in the blood if you're relying on PaO2 because it's not as sensitive and the stimulus to breathe isn't as strong, so CO2 will build up within the blood, which can then lead to obtundation and then worsening hypoxia and then eventually overwhelming obtundation leading to death. So that concludes this video, and in the next video we'll talk more about how all of these systems are integrated and go a bit more in depth into the physiology with some graphs on how hypoxia will change our sensitivity to CO2 and how CO2 will change our sensitivity to hypoxia. If you have any questions or want to leave any comments or anything you want me to cover, feel free to leave it in the comments and I will get around to responding when I get a chance.